Hello guys, I'm Hosayn Chibani, a PhD student from Laboratoire de Physique, University de 1945 à Ghana, Algeria. I'm gonna present my presentation titled as First Principle Investigation of Structural, Elastic, and Electronic Properties of Chromonitride monodiode. This is a quote from the father of nanotechnology, Richard Feynman. And this is the table of contents or the plan of our presentation. We begin by introduction, then we move to methodology, and then result analysis, and finally the conclusion. So the introduction: two-dimensional materials have sparked the interest of researchers since the discovery of graphene on 2004. These due to their unique properties compared to their 3D counterparts. But such family is peridotite, which has been synthesized recently on 2021, which found to be a Dirac semi-matter with two Dirac counts at Fermi level, like graphene. These results motivate us to study chromonitride from the same family using first principle investigations methodology. So we use the density functional theory as implemented in the first count. And when we use those parameters, so we use the GG plus U approximation with equal to 4.3. The energy cutoff was chosen to be 600 volt, and we used the cell with 15 angstrom perpendicular vacuum layer, gamma standard key point meshes, and conversion criteria was used to be 10 power minus 3 electron volt per atom for forces, and 10 power minus 6 electron volt for energy. Electron property was calculated with strain energy method. Then we move to discuss structural properties. As we can see from figure 1, the side view at the right, you can see that chromonitride is one atom thick and it is flat like graphene. This material shows a rhombic primitive cell with the space group, space group number 65, according to international notations, with last parameter as shown in table 1. So we see the value of A, B, and the AD gamma, which is defined as the angle between lattice vectors A and B. Furthermore, according to mechanical stability criteria for two-dimensional material with the rhombic cell, as we defined it in the rectangle at the right. So we find that the chromonitride is stable mechanically. So we move now for elastic properties. Elastic properties table 2 shows minimum, maximum, and anisotropy of Young's modulus, shear modulus G, and Poisson's ratio mu. As we can see this, this moduli shows maximum stiffness of 144 Newton per meter, and is an isotropic material. In other words, its elastic properties are orientation and independent. So to show this, we illustrated in the figure 2, the highest as we saw illustrated in the figure 2, the figure 2 orientation dependent Young's modulus E, shear modulus G, and Poisson ratio. So we see that the highest stiffness was found for 45 degree angle to x-axis, and the smallest one found for 90 degree angle to x-axis. And according to percentage ratio, this monolayer shows the highest flexibility when stretched along x-axis or 90 degree from it. Next, we move to electronic properties. So in figure 3, represent the first Brillouin zone, and the key path used to calculate the band structure was highlighted. According to density of states represented of figure 4, this material is metal and exhibit magnetic behavior. We can see that the density of state at the fermion is asymmetrical, so it is magnetic material. In addition, from band structure, there are the account along the high symmetry line, gamma to X, but above Fermi level for spin up channel, presented here in the figure 5 by red color. Be the formula for spin down channel, represented here by blue one. Yes, spin down channel represented by blue color. So this is the conclusion of our study. We find that the carbonitrile monolayer is metal and shell magnetism is cross-side, and it's stable mechanically, and it is shows anisotropic elasticity with a high stiffness along x-axis. From those findings, we can say that the carbonitrile monolayer is a good candidate for strain engineering and spin applications. This is some resources or references used to prepare these presentations. So thanks guys for your attention. Does anyone have any questions? So go ahead, I'm listening. Thank you, another time. Bye-bye.